Thanks, you. So thank you so much, Alexei. And thank you to GitHub and to Neo4j and to the other sponsors. I'm not going to take a lot of your time. I know it's late. People are tired. I'm tired. Everybody's tired. But I want to talk to you about the kind of experiment that we ran in the last couple of months at Pinecone, trying to kind of figure out what is a interesting kind of modality for us to kind of combine vector databases and vector RAG with graphs. And when I first read like the Microsoft paper on RAG, I was under the impression that it's going to be like this very, very specific architecture that follows like a very stipulated kind of recipe. And I really liked actually like the direction that's coming out of the Neo4j camp, which is graph RAG is kind of like a family of architectures, right? Like it's a family of architectures that combine a graph with some generative process and a retrieval process. And in our case, what we're trying to kind of do is instead of thinking of like an integration that takes the vectors into the graph itself, we're actually using the vector database to sort of create a focused subgraph from a much bigger knowledge graph that we create, and then use the graph and an LLM to generate and compose questions that are going to be interesting for the people who are sort of doing this exploratory kind of activity using the system. So when I first kind of started thinking about how to build this thing, my immediate notion was like, okay, I'll make an ontology, I'll take an LLM, I'll point the LLM onto my ontology, I'll combine it with the data, and everything is gonna just work. And no, that doesn't just work. What happens definitely without an ontology, right? When you're just sending out an LLM to look at a piece of text, and you just tell it, go build me a graph from that, right? What you get is a graph that isn't homogeneous in the sense that like the connections that form within it are sort of all over the place. And what that means is that basically you lose your ability to ask coherent, helpful questions out of that graph, right? The questions become a lot more one-off, right? You get a lot more variability in the types of nodes and edges. So nothing ever kind of consolidates into something that's actually usable. There's also like scalability challenges, which means you just create an explosion of types of nodes, types of edges, and as a result of nodes and edges that you didn't need in the first place, and kind of consolidating them is also a problem as well. So instead of that, we were like, okay, what will happen if we take a data set that actually already enforces some structure through its own metadata, that introduces some stable ontology that we can work around, and then limit the use of the LLM to the things that we know that it's really, really good at, which are two things. One is summarizations, and the second is generating queries, right? And I'll talk a little bit about how we did that in a moment. Just to give you a little bit of a taste of what the final product is, because otherwise this talk will be all in the air, right? What you see here is some user typing in an open-ended text question about the Supreme Court decisions. This whole experiment revolved around indexing and learning about Supreme Court decisions. On the left, what you see is we create the normal RAG path, right, which basically tells us for this given question which pieces of content actually match semantically, and then we summarize those, right? But in parallel to that, we also have some reference to nodes in the database that correlate to the same cases that we found in our RAG process, right? So what you see here is essentially that graph, that subgraph that is essentially a lens on top of the entire graph, focusing on specifically what the user is interested in. And then the second step is we use that graph, that subgraph that was created as a result of our initial semantic filtering, to construct questions that are then mirrored in a cipher query. And that cipher query is executable and has a good chance of actually returning with some actual result, right? That isn't just disconnected from the graph itself. And Again, I'll talk a little bit about like what the limitations of this are. Not every question that we generate actually results in a successful query, but as you see here, and many of them do. And in fact, when they do, the insight is quite helpful, right? In a lot of these cases, the question is indeed a follow-up question that could have been proposed by the professional to then and it correlates directly to the text that they found, which is again semantically relevant. Okay, let's go back to this. So how do we build this thing? So there are essentially 4 big systems participating in this. One is any kind of document store, and it really doesn't matter where you store the stuff when it's just metadata, just like JSON with a bunch of metadata. In our case, we just saved it in a Mongo instance. Again, it's important to note that the data that we're using in this case is essentially specialized, right? We're in this example, like I showed, we're taking Supreme Court filings, and those inherently have within them, and in that particular API that we're using, have within them structured information, like, for example, who were the justices who heard the case, who are the advocates who argued the case, where the case was argued, et cetera, et cetera, et cetera. So we are already starting from a place where we have some structured data to go off of. So the 3 other systems are a vector database, of course, a graph database, and an LLM that does exactly what I said, summarization and query generation. So as you saw in the demo, the components are a semantic search operation that, again, this is like the RAG we all know and love, right? But it has one extra step, and that is giving me back some handle onto the graph. And that is kind of like the crux of what's happening in this little experiment, is that we're saying there's going to be an asset, in this case the case IDs, which match between these 2 modalities, and they form our join bridge between those 2 databases. And that's how we're able to make some sort of get some sort of an insight onto the things that we've indexed semantically, and then leverage that insight on every consecutive query that we do on the graph. This is the overall structure of like the flow of this whole system. So we take the raw data as it comes in, we parse through that data, again, to just get those entities that we know are structured within the data, like advocates, cases, justices, and so on and so forth. We also do something a little bit additional to that, which is use good old-fashioned NER enrichment to extract additional entities and, again, associate them in a pretty strict manner back to those case entities, right? And that just gives us more opportunities to form more interesting questions about the same exact data without opening the aperture to an LLM that will start, adding types of nodes and types of edges willy-nilly. Instead, it's very, very limited to that subset of what the NER model can extract. And it just so happens that it produces better results down the line. Again, in parallel, we're doing chunking and embedding, like, again, in any other RAG process. And then when the application phase hits, we do our semantic search, and then that gives us back our document IDs or our case IDs. And then we do graph filtering, and then something pretty interesting happens, and this is where like our work with Neo4j really took shape, is based on that subgraph, we can now start doing some analysis on the graph itself to give us the best information to then pass on to the component that will do the cipher generation. Because if there's one component here that's a little bit iffy, right, in the sense that it's very fragile to like the inputs that it's getting and the quality of the output, it's the LLM generation and its ability to generate actual cohesive and meaningful queries. Yeah, I think this is already covered. Just to close off, before I'll take some questions, the stuff that we want to keep kind of looking into with this experiment. So as you saw, we do these sort of intermittent steps that are divided by some human interaction. So we start with a semantic search, and then we get back results. We choose one of the cipher queries, and they give us back some insight. That process in and of itself could be, quote unquote, automated with agents, basically allowing these agents to perform the cipher queries themselves, even correct them if they're getting back no results or bad results, and try again with better query generation. So that's one area that we want to explore. Of course, using richer data sets that are much more highly interconnected is something that we're looking at. Using much bigger ontologies and pointing the LLMs to them so far hasn't worked really well, but with Alexi's help, we're going to crack that nut as well. And yeah, I think that's basically it, if anyone has any questions. Thank you.
As usual, raise your hand, I'll bring the mic to you.
This is more like a hypothetical question. So I've worked in knowledge graph like almost like 6 years. So I would ask the question as like, imagine you have unstructured text like the internet. So what do you think would be the effort like to like say take that unstructured text and build your own ontology based on understanding topics and then like I don't know and use LLMs to like create a knowledge graph, web scale knowledge graph out of unstructured text like the actual the internet.
Just for the entire internet, though.
I mean, it could be a smaller set, but I'm saying in terms of understanding topics and creating like say objects and property graph. I mean nodes and splitting them.
The thing with ontologies is that that's exactly what they're like. They're a set of terms, right, that help us understand a domain, right? So you can expect that for every domain that you want to cover, you're going to have to create some ontology for that domain, right? And I think that's like one of the biggest challenges that the graph community has had in general, at least. How do you generalize any kind of canonical knowledge graphs? And there's been obviously like many attempts in the past, and none of them really stuck because it's like all like people have their own opinions about what and it needs to happen. It's really hard to reach consensus. I think the question is, how do you reliably create a mechanism that can create an ontology on the fly, but also not let it diverge in really weird ways, right? So like I want the LLM to understand my data on an ontological level, but right now it can't quite do it because it kind of like fritzes out and kind of it gets lost, right? Even if you give it like very particular things to focus on, it doesn't quite do it a great job at that just yet. So I think that there's still a lot of room to research.
Other questions? If not, let's thank Roie again. Yeah.